So I have started the recording now. Now I'll share my screen. Okay, so hello everyone. Welcome to Week 5 TA session of NPTEL CS52 Reinforcement Learning course by Professor Balaraman Ravindran from CSC Department IIT Madras. I am Sandarbh Yadav from CSC Department IIT Bombay. And this is the Week 5 session conducted on 23 February and on Friday. Like usually this was supposed to be on upcoming Tuesday, but it got preponed to Friday. So again, it was supposed to be on Tuesday, but it got preponed. So the next one, which we will have, will be on 5th March, Tuesday, right here. And this will be for week 6. So again, like the same link, and anyone who has taken this course can attend this. So we will discuss practice assignments, and do some problem solving and doubt clarification. But either way, like this is going to be a recorded session, so there's no two-way communication here. So expectation is again like same as previous weeks, that you should have watched the weekly lecture videos, attempted the weekly assignments and practice assignments, and also like you can read the book. It is recommended to read the book, and these slides and recordings will be made available to you. So again, guidelines. So basically, like we will be following the same order as usual: practice assignment, then problem solving. Like these problems will be different from practice assignment and assignment, and in between we will do demo of like this week. Like last week we did value equation. This week I'll show policy equation, and then like the assignment. Okay, so big 5 topics are LPI convergence, in which it was proved that this operator LPI, which is the Bellman operator, it converges. Then we use Bellman optimality operator, which was denoted by L, to like kind of introduce this algorithm value iteration. And then we moved on to policy iteration, in which we worked in the space of policies, then dynamic programming section. And afterwards, like we moved to the next chapter, which is Monte Carlo and control in Monte Carlo. So these are the topics for week 5. So let's begin with the practice assignment. So the first question says, let the policy and value function obtained by applying policy iteration in a finite MDP be pi n and v pi n. So after the stopping criterion is met. So while like we have almost converged, like we have actually converged, this is the like final policy which we have obtained, which is denoted by pi n, and the corresponding value function is b of pi n. Then like we have to like kind of argue like which of the option is correct. So pi n will be the optimal policy, but b pi n might not be the optimal value function. So this is not possible. If pi n is the optimal policy, then the value function corresponding to it should be the optimal value function, right? Pi n might not be optimal policy, but vn will be the optimal value function. Again, the same similar kind of argument in reverse direction. This is also not possible. Then the third one says nothing can be said about pi n and v pi n. This is also wrong. So pi n will be the optimal policy and v pi n will be the optimal value function. This has actually been proved in the lectures, right? In which the like proof was derived based on intuition. Like there are like finite number of policies, and in each iteration we are moving closer and closer to an optimal policy. So eventually like we will reach the optimal policy, and the p pi n corresponding to that optimal policy will be the optimal value function also. So this is the correct option here. So now the second question is, Monte Carlo policy evaluation must use exploring starts in case of non-deterministic policies. Like basically this is a assertion reason kind of question, in which you have to see like the validity of these assertion and reason. So first of all, like assertion is definitely false because like exploring starts are used in case of deterministic, not non-deterministic, because non-deterministic, like it kind of due to uh, like stochasticity, like it kind of ensures that we explore enough. So it is necessary in case of deterministic policy. And the reason is they have given is they have to rely upon exploring starts in the case of non-deterministic policies to ensure adequate sampling of all states. So in case of non-deterministic policies, that adequate sampling of all states is either way happening because of the stochasticity. So we don't need that. So this is valid reason if it was deterministic policies. So both like assertion and reason, both of them are false. So now I will move to the third question. So the third question says, which of the following is are guaranteed to be true at the stopping criterion for value iteration? So here we are talking about value iteration, and this is the stopping criterion which we have used. So basically, like when the norm of the difference between two successive value vectors in the like vector space of value functions, this becomes smaller than this quantity, then we kind of stop. So which of the following are correct? So first option is like v pi minus v star norm is lesser than epsilon. So is this correct? Yeah, like this is basically a multiple option correct. So squares denote multiple option correct. So this usually happens like this we have derived in class, like we used triangle inequality and first one came out to be lesser than epsilon 1 2 and the second term also came out to be lesser than epsilon by 2. So in total like this will be lesser than equals to epsilon. Now the second option is uh, Vn plus 1 minus V star is lesser than or equal to epsilon. So in again in class, so this was one of the term there, like we distributed over it. So what we need to see is like we have actually derived in class that this is actually the option D. We have which we have proved in class. Vn plus 1 minus V star, the norm of this difference between vectors is lesser than epsilon by 2. So if it's lesser than equal to epsilon by 2, it will definitely be lesser than or equal to epsilon. So D kind of implies B here. So B is also correct. But here the third option is V pi minus V star is lesser than or equal to epsilon by 2. This is wrong because V pi minus V star has to be lesser than or equal to epsilon, not epsilon by 2. So now I'll move to the next question, which says, consider an MDP where there are n actions. So we are working in an n action space and each of which is applicable in each state. So from all of the states, we can take each of those n actions. If pi is an epsilon soft policy for some epsilon greater than 0, and q pi is the action value function of policy pi, then consider the following statements and choose the appropriate option. So this is the setting we are given. And again, the question type is assertion region. So any epsilon greedy policy with respect to q pi is strictly better than pi. Is the assertion false or true? Any. So the important thing here is any. Will it be like strictly better? It need not be strictly better. So the general sign is it can be better or it has can be equal to also. So strictly better is not there. So this assertion is false. And the reason which they have given is in an epsilon greedy policy, the action with maximal estimated action value is chosen with probability 1 minus c plus epsilon by n, and other actions are chosen random with probability epsilon by n. So this is true, right? I'll explain how this happens. So with epsilon probability, we are exploring, right? So there are, since there are n actions, so we will distribute this epsilon by n to all of the actions, but this will contain one optimal action also, right? This we saw in the case of bandits also. So, but we are exploiting that optimal action with probability 1 minus epsilon. And now like this epsilon by n also gets added here. So it becomes 1 minus epsilon plus epsilon by n. So with this, like we are like choosing the maximal estimated action value, and like other actions are chosen with just simply epsilon by n. So this kind of ensures exploration. So although like assertion is false, but the reason is true. So the correct option is assertion is false, but reason is true. Option C. So now I'll move to question number 5, and this is the last question of practice assignment. So if V satisfy LV, so L is the Bellman optimality operator, and L pi is the simply the Bellman operator. So L pi converges to V pi and L converges to V star, like optimal value function. So the question which they have asked is pi is epsilon optimal and V is the fixed point. So first of all, like we can say from here, they are asking for pi. So let's see for pi. So L pi V is equals to V. This basically kind of implies that V is the optimal like fixed point for this policy pi. So this option is incorrect, and this option is also incorrect. No, no. So basically, like the option which says V is not the fixed point of pi, this is definitely incorrect. Now we are also given that LV is equals to V. So this happens when we have converged to an optimal policy, right? And this is also equals to L pi of V. So this basically means that pi is the optimal policy, right? Then only this will happen. So pi is an optimal policy. So again, like it is an optimal policy. So this says non-optimal. So this gets cut. This is epsilon optimal, not epsilon optimal. It is actually the optimal policy. So this is the correct answer. Pi is an optimal policy and V is the fixed point of pi. So now I'll move to problem solving section. So first question in problem solving section is this. For a particular finite MDP with bounded rewards. So rewards are like bounded, like some are max to R max range. Like we be the space of bounded functions on S. So this is the usual space, and this S is the state space of the MDP. So and let pi be the set of all policies. So pi is the set of all policies, and let b pi be the value of the function corresponding to policy pi, where pi belongs to this set of policies. Is it true that v pi belongs to V for every policy pi belongs to pi? Like it has to be true, right? We know this space V, like it is a space of bounded functions. So all the like value functions will be some points in this space, right? And there might be some extra points also, like which might not correspond to value function. But the question this is asking is that for every policy, like will v pi corresponding to it will be in the space? Yes, it will definitely be there. But there might be some extra points, but all the v pi will definitely be there for all policy pi. So this is correct. So now I move to the second question. So in the proof of the value equation theorem, we saw that LV of n plus 1 is equals to L pi of V n plus 1. Is it true in general that for an arbitrary bounded function, like this is the important thing. Does this hold for any arbitrary bounded function? So this shouldn't hold for any arbitrary. Like in the proof, we assume some special conditions, right? Like one of the condition, like we assume like pi was chosen in a careful manner. So what was pi? The pi we chose was like this. So this is like the action corresponding to state S was arg max over actions, and this is the expectation over reward given we are in state S and we took action A plus gamma times summation over S dash. Like these are the like set of next states which we can visit. Then the probability of visiting that state by taking action A from state S, and what is the like probability associated, like what is the value associated with that state S dash. So we were choosing in a greedy manner this policy with respect to current estimate of value function. So like will this hold for any arbitrary bounded function B? No, it won't hold. If we choose like in this way, like then only it will hold. So the answer is no. for any arbitrary bounded function, it won't hold. It might not hold. It might hold, but we cannot guarantee that it will always hold. So again, like continuing with the previous question, why is it the case that LVN plus 1 is equals to L pi Vn plus 1 in the proof? Because the equality holds in general. This we have already said that it doesn't hold in general. Can hold, but like you cannot say that it will always hold. Because Vn plus 1 is the optimal Pauling function. No, again, this is not the reason. And like because we are considering only deterministic policies. So like see, we were considering this deterministic policy, right? Because we were not, we are mapping to only one of the states. So we can consider like there was a result which says that for finite MDPs, like in finite MDPs, we definitely have an optimal deterministic policy. So we were considering deterministic policies and choosing a max valued action in each state. So this we were already doing. See, like for each state, we were choosing this max valued action. So argument of max will return the action which has the max value. So this we were doing. And the fourth option is kind of irrelevant. Vn plus 1 is not a value function. It is definitely a value function. So answer is C. So now I'll move to the next question. So it is given that Q pi of SA, like action value, is greater than like for some state and for some action is greater than V pi of S. What we can conclude? Action A is the best action that can be taken. No, we cannot say action A is the best action. But what we can say is that A is better than pi S. Like whatever action this policy is suggesting, A is definitely better than that action. But it need not be the best. There could be some other action A dash which might be better than A. So we cannot say this. We cannot do this conclusion. Pi may be an optimal policy. Definitely, pi is not an optimal policy, right? Because we for this state S, like there exists an action which is better than the action suggested by the policy pi. So pi is not optimal policy. So the third option says pi is not an optimal policy. So this is actually correct. Like pi is not an optimal policy because if it was optimal, it should have suggested this action A instead of whatever like action it is suggesting as of now. So pi is not an optimal policy because pi should be suggesting actions which have the highest Q values and none of the above. Again, this cannot hold because C is true. So now we will move to the next problem. And this problem is from the last lecture. So last week, I shouldn't say last week, but essentially like the live session of week 4, which happened on last Tuesday, we discussed this problem, right? In which like there was a laughter state in a ghostly house and quiet state, and like O denotes playing organ. So organ is a musical instrument, and I denotes using incense state. So we saw this problem and like this is the MDP which we constructed last week. So I have simply taken it from last week. So there was a laughter state. So we can move from laughter state to quiet state only by playing organ, regardless of whether we burn the incense stick or we don't burn the incense stick. And this way, like we whenever we play the organ, we were landing in quiet state. And for if we don't play organ, then we definitely won't go to quiet state. We will remain in the same state. And if we are in quiet state, then the only way we will remain in quiet state is like if we don't play organ and like burn the incense stick, then only we will remain in this quiet state. And all the other for all the other combinations, like we will go to laughter state. So if we play organ, then definitely we are going back to laughter state. Obviously, like this is natural also because of the problem specification, which was discussed in last week. And the last section also, like if we don't play organ and don't burn incense stick, then also we were going to laughter state. And for all the transitions which are coming into laughter state, the reward is -1 because like laughter is something which the author of the letter, like there was a person who sent a letter to you to help him solve this MDP. So that person want his house to be quiet. So laughter, like for all the transitions which are coming into laughter state, the reward is -1. And for all the transitions which are coming into quiet state, like these three transitions and this one self loop. So for this, like reward is +1. Like because this is desirable situation. So this is the recap of the problem which was discussed in last time. So now what I'll do is I'll read the problem statement. So recall the problem described in the first question of the previous assignment. Yeah. So use the MDP formulation arrived at in the question and starting with policy pi laughing equals to pi silent. And so basically they have given us an initial policy. Let's call this pi naught. Also, one thing to mention is like I'll mention the discount factor. So discount factor in that problem was 0.9. So remember this, we will be using this quite a lot. So they have given us some initial policy that when you are in laughing state, you should burn incense and no organ. So basically no organ and burn incense, which means we are remaining in laughter state only. And if you are in silent state also, then also same action. So burn incense and no organ. So this basically means uh, burn incense and no organ. So again, if you are in quiet state, you remain in quiet state. So the initial policy which is given to us is if you are in laughing state, like take this action and remain in laughing state. If you are in quiet state, take this action and remain in quiet state. Now, what they are asking is to perform a couple of policy iterations or value iterations. And the important thing is by hand. You don't need to use algorithm for this until you find an optimal policy. Okay, and this is a kind of remark that if you are taking a lot of equations, stop and reconsider your formulation. Maybe like the MDP you formulated is wrong. So basically, like they know in hindsight that the answer is something which can be reached within a few equations. So if you don't read, this means that your MDP is incorrect. So what are the resulting optimal state action values for all state action pairs? So they have given us some action values for states and action pairs, and they are asking us which of these options are correct. So let's begin. So as I mentioned in last lecture also, there is, so basically I'll start with this. So there are 5 components of an reinforcement learning problem. Basically, these are the 5 components of MDP also. S is the set of states, E is the set of actions, T is the transition probability, R is the reward function, and gamma is the discount factor. Now, what happens in planning? So currently we are doing planning setting. So in planning setting, generally there are 3 approaches: value iteration, policy iteration, and LP. So LP is it is an optimization technique, but it is not actually a reinforcement learning technique. But basically what happens is we reduce that solving of Bellman optimality equation problem into an LP, like with proper objective function and proper constraints. And there is a dual formulation also and a primal formulation also. And this LP, after formulating this LP, we give it to the an LP solver. And then there is a popular LP solver called Pulp. So this LP solver will return us the solution, and we will kind of do the reverse mapping and get the optimal solution. So this is also one popular way of solving this MDP. But in this planning setting, we have access to these transition probabilities. But in actual reinforcement learning, learning setting, which is quite often called control also in the control literature, in this we don't have access to this transition function. So states, we know actions are in our control, reward we get from the environment. So states is also supplied by the environment. So in learning setting we don't have access to this transition probabilities, but in planning setting we have access to transition probabilities. So what happens in planning setting, it basically becomes a computational problem. Kind of we need to simply compute, no need of learning. But in control setting we actually learn by interacting with the environment. So in this slide, I have given you the policy iteration algorithm. So how this operates is there are 4 basic steps. So first we begin with some initial policy. So in this problem, we have been given an initial policy itself, which says if you are in laughing state, take this action and remain in laughing. If you are in silent, again take the same action and remain in quiet state. If you are in quiet state, so basically you remain in the same state. this is the initial policy given to us. Now what we do is, like, this is the iterator variable, so n equals to 0. So what we will do is, first we will evaluate the policy. So evaluating policy basically means like computing its v pi. So suppose for policy pi, we will compute its v pi. And how we calculate this v pi? Either like you can use the Green's equation, like this was discussed in one of the previous lecture, that in this way like you can calculate the value function, like, or either way, like second way is to do it iteratively. So we will like keep on applying this pi operator until it converges to a fixed point. So these are the two ways to do it. So in like this problem, like I'll be using Green's equation to for policy evaluation. And then once we have evaluated the policy, then we will choose a policy pi, new policy, updated policy at n plus 1 step, which will be greedy with respect to this evaluated value function. And in this way, we will select it. And we have to do this component wise. Like this has been written in vector notation, but you should understand that this is a component wise argmax. And one important thing to note here is that consistent tiebreaker criteria is needed. Suppose at some, like you are using arguments right here, so it belongs, like it is using belonging to, not equal to. So if suppose there are 5 actions which have the same value and you choose one of them, so keep it consistent in future iterations also. So the basically the tiebreaker criteria should remain consistent. Otherwise, if you are like choosing one action in one equation and in next iteration you will choose some other action, and it will kind of, the policy will keep on oscillating between these actions. So it won't converge. So important thing is to like keep this tiebreaker criteria fixed. And we will see this in our example also, that this comes up. And this is the like stopping criteria. We need to stop when the next policy derived is same as the previous policy. So if like for all the states, like after following this uniform tiebreaker criteria, all the states are mapping to the same actions. So like suppose if S1 is mapping to A1 some action, and this is happening for both of these. And in a similar way, for other states also, like the same mapping is there, then we say that these two policies are equal. If this happens, then we will simply say that we have reached the optimal policy and we will declare it as the optimal policy. And if it just doesn't happen, then we go back to step 2 from here. And again, like keep on repeating this procedure until this criteria is satisfied. So this is the like brief overview of policy iteration algorithm. So now like this is the like initial policy which we are starting with, like pi naught. So in laughter state also and in quiet state also, we have been like, this has been supplied to us that you need to start with this action. So these are the like initial policy. For laughter state, we also like don't play organ and burn the incense stick. And for quiet state also, like this is the case. So in both of these cases, basically what happens in MDP is, if you are in laughter state, then you remain in laughter state. If you are in quiet state, then you remain in quiet state. And also, like in policy evaluation, we will need this value function. So we will initialize it with 0. So both the components are 0. So our value vector is corresponding to, even first, we will denote the first component as laughter and second one as quiet. So both of them are 0 as of now in the initialization phase. Now we will perform the policy evaluation. So this is the like the first iteration. This we are doing first time. So you see, like in policy iteration, like there are these steps, like these we have to keep on repeating. So this is the first time we are doing this for policy evaluation. So this is the identity matrix. It's 2 by 2 because like we have 2 states only. So again, like the first one corresponds to laughter and second one corresponds to quiet. Minus. So this is basically the Green's equation, right? And Green's equation basically computes this v pi naught. So initially, like we have to compute this value function corresponding to pi naught, because this is the policy given to us. Then we will like improve this policy pi naught to pi 1. And in the same way, like we will keep on improving until like the stopping criteria is there. And in this way, hopefully, like there will come a condition where pi n plus 1 will be equals to pi n. Then we will like kind of stop our algorithm and say that this is the optimal policy. So basically, like in this Green equation, it is I minus gamma times. This is the transition probability matrix, right? So basically, like what is happening? So if we are in L laughter state, then we move to laughter state according to this policy with probability one. We remain in laughter state. We don't move to quiet state, right? So the probability here is zero. And for quiet state, we don't move to laughter state. We stay in quiet state. So here the probability is one. So this is the transition probability matrix, and we have to take inverse of this, like as we saw in the last slide. So I minus gamma p pi n, like inverse, and the next is the rewards. So again, like we saw this MDP, right? So if we are in laughter state and we remain in laughter state, then the reward is -1. And if we are in quiet state and we remain in quiet state, then the reward is +1. So again here, so first one corresponds to the laughter one, so -1 and then +1. So this basically we have to solve. So this is the like simple setup for Green's equation. You can like compute this matrix and it comes out to 0.1000, and you need to take the inverse of it. That when you take the inverse, it comes out to be 10, 0, 0, 10, this matrix, and you multiply it with -1 and +1. So you get this value. So this is our like V pi naught. So first one like this corresponds to laughter state, and this corresponds to quiet state. So this is the value corresponding to this policy pi naught, which is already given to us. Now we perform the policy improvement. So what happens in policy improvement? So in policy improvement, we basically component wise, we will select that action. So this is given in terms of vector, right? This is n plus 1. This is given in terms of vector. So what we will do for some state s, we will select the action which basically maximizes this quantity. So for we have to do for all the states, right? Either way. So first we do for L state. So these are the like four actions which are possible: playing organ, burning incense, playing organ, not burning incense, not playing organ, and burning incense, and doing nothing. Like basically not playing organ also and not burning incense stick also. So again, we saw that whenever we play organ, so like this is the R plus gamma times value, right? So this is the quantity which we need to compute, and this value will correspond to this policy. So we can write pi naught. So the reward, whenever like for the first two actions, whenever we take these first two actions in laughter state, we go to quiet state, right? By playing organ. So the reward will be +1 for both of these. And gamma factor, as I have already told before, that it's 0.9. And then like we supply the values. So in first two, like we are moving to quiet state, right? So when we are moving to quiet state, the value of quiet state is +10. So we are doing that. And for the remaining two actions, we were remaining in laughter state. And when we remain in laughter state, like our reward is -1. And also the value corresponding to laughter state, according to this policy pi naught is -10. Now, when we solve this, like we get value +10 and +10 and -10 and -10 for all the four actions. So which one is optimal action? So these two are optimal actions at this step corresponding to pi naught. So now we have kind of basically deduced like this, these will be the optimal action for pi 1, like because we are improving our policy from pi naught to pi 1. So keep in mind that like as of now we are using deterministic MDPs. Otherwise, like you could have like distributed some probabilities to both of these, like maybe 0.5 to this, 0.5 to this. But as of now, we are dealing with deterministic MDPs. So basically deterministic policies. So we will like basically I mentioned in the last slide that we have to fix a tiebreaker criteria and then remain consistent with it. So either you choose this one or this one, and like keep it the same in the future iterations, but don't like keep on switching between these two. So initially you choose one and remain consistent with it. So we can do this. Now, like similar procedure we will do for Q state. So now in quiet state, what happens again? We have the four actions. So in quiet state, the only way we can go stay in quiet state is by taking this action. We don't play organ and burn instance sticks. So in this case, the reward is +1. And again, like similarly, like this is the discount factor 0.9 for all. This is same. And when we remain in quiet state, like the value of quiet state is +10, like we saw this. And similarly, like for all the other three actions, the reward is -1 because we were moving to the laughter state. And in laughter state, the value is -10. So correspondingly, when we do the calculation, like it comes -10 here, -10 here, -10 here also. So this is the optimal action at this step. So now, like we are in the policy improvement phase, so we have to like select a new policy. So we have determined that like for quiet state, this is the like action which is actually maximizing it. So this is what will be written by the argmax. And for that one, laughing state, there are two possibilities. So the thing is like you choose one and remain consistent with it. Don't like switch from one to another. So now we do this. So either you choose this, for example, like I have chosen this, you could have chosen this one also, but fix one and continue with it. So our new updated policy pi one. So for laughter state, we will be choosing action, play organ and burn incense stick. And for quiet state, we will be choosing don't play organ and burn incense stick. So this is our pi one policy. So again, like we can do stochastic policy also, but here we focus on deterministic policy because like our MDP is finite, right? And we know our result which says that for finite MDPs, we actually can like find a deterministic optimal policy. There can be stochastic policies, obviously, but a deterministic policy will always be there. Now, like uh, we compare again. We have that stopping criteria, right? Our policy pi one, is it same as pi naught? No, it's not. Because pi naught, like the actions were this, and here like the change has happened at L state. So pi one is not equals to pi naught. So we need to like again go back to step two of policy iteration algorithm and start with the policy evaluation again. So in a similar way, like this is the identity matrix. Now like response factor same. Now what happens? If you follow this policy, what this policy basically says, like if you are in laughter state, then by taking this action, you are moving to quiet state, right? And this is quiet state. And if you are in quiet state, then by taking this action, you remain in quiet state. So basically, like in both the cases, you are moving to the quiet state. So our transition matrix will be like, if you are in laughter state, you don't remain in laughter. You supply all the probability to quiet state. And if you are in quiet state, then you have no probability to laughter state. You just remain in the quiet state. So this is the transition matrix for us. And we simply like have to calculate the inverse of this quantity. This is I minus gamma times that transition matrix, P corresponding to pi 1. And again, like the rewards. So we also know that any transition which lands in the quiet state has a reward of +1. So this is our reward vector. Now, like we calculate this, so this comes out to 1 minus 0.90, 0.1, and we have to take the inverse of it. So inverse comes 19010, and we multiply it by the reward vector. So now, like our value function becomes this. So this corresponds to laughter state, and this corresponds to peak state. Now, in the policy improvement step, which is next, we will be greedy with respect to these v value, not like the old ones. So now we will be greedy with respect to this value function. Now this is the policy improvement step. Again, like we have to do for both the state L and Q. So L and Q, like these are the four actions. So if we take like if we play on and then we know like it will be +1 and we move to quiet state. So either way, like in this case, like all the states, like both the states use, so like even the laughter state and quiet state have the value same 10. So we don't have to worry about the value. Gamma factor also remain consistent. We just have to worry about the reward. So if we take play organ and regardless of whether we burn incense stick or don't burn, we get a reward of +1 because we are moving to quiet state. And otherwise, like if we don't play organ, then we remain in the laughter state and reward is -1. So if we calculate it, like it comes out to be 10, 10 here, 8, 8 here. So these are the optimal action at this time. Again, like as I mentioned in the previous slide also, that you have to remain consistent. So if you chose this one as the tiebreaker criteria, you choose this one again in this situation also. Don't switch to this one. Otherwise, like that policy will oscillate. For the remaining, it's 8. Now we see this one for quiet state. So for quiet state, only like one transition was +1, which is this action. And so in that action, we get a reward of +1 because we stay in quiet state. For the remaining actions, like we were moving to laughter state, so we were getting reward of -1. And in a similar way, when we solve, like we get 8, 8, 10, and 8. So this is the actual optimal action at this step. So now we have to improve our policy. Now we come with pi 2. So pi 2 basically like we are keeping consistent with the our criteria. So I selected this. You could have selected this, but don't switch between them. If you select this, continue with this one. So this is also a possibility. You could have gotten this answer here, but don't switch between them. So I have selected this one, um, like playing the organ and burning the incense stick. So I'm being consistent with it in the tiebreaker criteria. So I'll keep this. So for laughter state, this is my optimal action. And for quiet state, this is my optimal action. So now we compare, like we find that in Pi 1 also, like these were the optimal actions, like playing organ and burning incense stick, playing organ, burning incense stick for laughter state. And for quiet state, it was not playing organ and burning incense stick, same thing. So Pi 2 equals to Pi 1. So basically like now we have reached the stopping criteria. So this basically means our Pi 1, or you can say both are equals to Pi 2. These both are equals to Pi star. This is the optimal policy. So this like in this way, like we have done few equation of the policy equation. So how many equation we needed? We needed just two equation. So this is like a very important example because like these it actually shows you how to use this value iteration and policy iteration algorithm. So next we will see value iteration. Because that like the question has asked us to do both, perform a couple of policy equation or value equation. So we are doing both so that you get an idea how to do this. So again, like I'll give you a brief overview of value equation. So again, here also we begin with some initial value function and epsilon, we pick some epsilon. This is for the stopping criteria, which we see here. And let n equals to 0. This is the iterator variable. So for each state, we calculate this new like this is basically the Bellman optimality operator. So this we have written component wise for each state. Otherwise, like in vector form, it will be written like this. So this basically basically the intuition is we keep on applying this Bellman optimality operator again and it converges to V star. So this is the idea here. So for each S like this, we have written in a component wise manner. And the stopping criteria here becomes is like the norm of difference between these two consecutive value vectors, like is less than this quantity. Then we go to step 4. Otherwise, we repeat the step 2 by incrementing n. So n like is a iterator variable, like you increment is n plus 1. Now, if we like we have converged, we have moved to this one. Fourth step. Now what happens is now we can obtain the policy from the optimal value function. So in this, like if we have converged, we have definitely reached the optimal value function, and then we like use this equation Argmax of this quantity to get the optimal policy. So this is the simple value iteration algorithm. Now I'll show you like how to actually use this value iteration algorithm for solving our MTP. So again, like the initialization phase, we start with 0 initialization for laughter state also and quiet state also, we have 0. So this is our value vector initially. Now you can do it in terms of value, like in terms of vectors, but I'm doing it component wise. So this is the like first iteration of value iteration. So first iteration, like we need to do for all state, right? You saw here for each state we have to do this. So we have two states in our problem, laughing state and quiet state, and each of them have the 4 actions. So basically, like in this, like we have to select the max value, right? In policy, we were doing arguments because we wanted the action which was achieving the highest value, but here, like we simply want the value because we are using value equation. Value equation doesn't involve policy much. Like at the last step, only like when we have reached the optimal value function, then only we can deduce the policy. And in between, like we don't need the policy. So what we are doing is like for the 4 actions, again, this is similar. So we have started with this value function 0, 0. So again, these are the, if we play organ and regardless of whether burning incense or not burning incense, we get reward of +1 and we move to state. So either way, like for both the states, the value are 0. So this remains same. Discount factor remains same also. And for like, if we don't play organ, then we were remaining in laughter state and we were getting reward of -1. So when we solve this, we get this one, right? And like remember, like here we are not worrying about which action gave that value. In policy iteration, we were kind of worried about like which action was giving the value, and we were maintaining some tiebreaker criteria. So in value iteration, we simply care about the value. So V1, this is one not dash. So V1 of laughter state will be the maximum value, and it is 1. And in a similar manner for Q also, like in this section, like we will get a reward of +1. Otherwise, like when we are moving to laughter state, we get reward of -1. And other entities remain same. So on solving, like we get this one. So V1 of Q also is 1. So now vector becomes 1, 1. So this is our next vector. So this is V1 vector. Okay. So now we have moved to V1 vector. But again, like our convergence, uh, we don't worry about convergence in value iteration either way, because like we have this convergence criteria. We haven't set an epsilon. So we are like just trying out initial few iterations and see how, if some pattern emerges. If some pattern emerges, then we take advantage of that pattern. And as we will see, like, a pattern actually emerges. So again, like we do the second iteration. Now in second iteration, we will be using V1 here, not V0. So V1 was 1, 1. So again, like both the states have the same value. So this remains same. Gamma discount factor remains same. Again, like the same rewards. If we are playing organ, like in this case, it's the first two actions is +1, and for the other two actions it's -1. And you know why we are not considering multiple states, because our MDP is such that it is like the transitions are deterministic, right? If we take some action, we land on in only one of the state. It's not like in a probabilistic manner. So due to that, that summation is not coming. So basically what is happening, with one probability we are going to some state, and with zero probability we are moving to other state. So it's like kind of uh, extreme case. So now in a similar manner, like we can do for this quiet state also, like for this third action, we will get a reward of +1. For the remaining actions, we were moving to laughter state, so we get -1. And when we solve this, like we get 1.9, 1.9. Again, like we are not interested in which action is generating this 1.9. We are simply interested in this 1.9 value. So we like now we are reaching V2. Like this is our second value function, which is at the second iteration. So V2 is the vector, not square. Don't read this as a square. This is the second iteration. So I am using superscript instead of subscript. And in a similar manner, you can deduce for quiet state also that the value is 1.9. So for again, like our vector remains 1.9, 1.9. So both the states have the same value again. So now we do like, also you can see 1.9 is like basically like this, you can see from here also, it's coming like 1 plus 0.9. So 1 plus 0.9. This like this is the how a pattern will emerge. Now let's do one more iteration. So this is the last iteration which we will be doing. We will like after this iteration we will see a pattern. So again, like for the laughter, now our vector becomes 1.9, 1.9. So since it's same for both the states, again, like we have the same 1.9 values here, same discount factor, and reward also same, like for these two actions it will be +1, and for the remaining it's -1, and for quiet state it will be +1 for this action and -1 for the other one. So now again, like when we calculate, we get 2.71. So now we have moved to V3, third iterate value function, and this comes out to be 2.71. And this 2.71 you can write like 1 plus 0.9. See how this happens. Like if you break this 1.9 into 1 plus 0.9, then 0.9 multiplied by 0.9 and plus 0.9 square. So and like similar kind of thing is happening here. So now what is this? This is a GP, right? This is the first term, and this is the common ratio. We are getting terms multiplied, right? So our value function is basically sum of n GP, and ideally, theoretically, like we should be doing this till infinity. So the sum of an infinite GP is a upon 1 minus r. So a in our case is 1, right? And common ratio is 0.9. So 1 minus 0.9. Also note this common ratio is less than 1. If it was more than 1, then it would have reached infinity, this summation, because it keeps on growing and growing. So this will become 1 upon 0.1, which comes out to be 10. So this 10 will be for both these states. So in the limit, like after we do this, keep on repeating this value iteration. Although we are not doing manually, but we saw a pattern, and on the basis of that pattern, we realized that this will proceed in this manner, and it comes out to be. So our optimal value function is 10 value for both the states. And again, notice like in policy iteration also, we got the same value function, right? Where did we get it? So we got it here, policy evaluation, just before termination. So here also it was 10. So these two algorithms are consistent with each other. But like this, we have demonstrated how to like perform value iteration and policy iteration. But the question is, are we done with this question? Because this question asks something else, right? Like this is the way which in which we do it. But the question was asking about optimal state action value, basically Q values, right? So now we have one more step to do. Like we have reached the optimal V star. Now from this V star, we need to derive this Q star. So let's do this. So how do we do this? So this is like one of the most important question, like in this whole today's session, because this will actually teach you how to do value iteration and policy iteration. Like if you do it in an algorithmic manner, either you like code it through or you can understand the dynamics from it. So either way, like we have the demo on both of them in the next section. So if we have like V star, and we can easily compute Q star of SA by this equation. So what we are doing is we take first step according to this action. So first time step, we take this action. So this is like, otherwise it would have been biased. So here like we are moving in an optimal manner. So this action A, then the reward which we get, and again this here A comes, and this is the optimal value function. So this we have to calculate, and this I'll show how I have calculated. So see, the thing is like this is not needed, right? Because like we are either way moving to just one state. So this probability will be one for exactly one state and zero for the other. So either way, we have only two states. So like basically it's one for one state and zero for the other state. So if we have like these are the like possible combination of like Q value. So S A, this is the Q value pair. So if we are in state L and we take action this one, O like playing organ and burning incense stick, then we like playing organ simply means then we land in quiet state. So in both these cases, like what is the quantity like we reward we got is +1 plus gamma discount factor, and this is the optimal value function. So for the quiet state, it is 10, although it's same for like both the states. So we have used the same value here. So this comes out to be 10. And similarly, we do for other actions also, but the only difference here will be this -1. Because in this way, in this, like if we take these two actions from laughter state, then we remain in laughter state. So in any transition which was going into laughter state was getting a reward of -1. So due to this -1, it becomes 8. So now like we have our like Q value function. So Q value function, like if the state is L and the action taken is L, then the Q value is 10. 10. And for these two actions, it's 8, 8. Now, similarly, we can do for quiet state also for all the four actions. So here we will get for this third action, we will get +1. And for the other actions, it will be -1. So in a similar manner, like we get 10 here and 8 for other. So again, like basically the optimal action is whichever has the highest Q value. Right. So in this like quiet state, this is the optimal action because it corresponds to 10. Other actions are giving Q value of 8. And for the laughter state, we have two possibilities. We can choose any one of them. So now we move back to the options which were given to us. So the options were like Q star of SA, all states, all actions. Was it 8? No, it wasn't. Was it 10 for all actions? No, it wasn't. Was it like they are saying for optimal action, it is 10, and for non-optimal action, and so A star basically denotes the optimal action. So for non-optimal action, was it -10? No, it was 8 actually. So this is the correct answer. So for optimal actions, we were getting 10. For suboptimal actions, we were getting 8. So this is the answer. So you see, like this is one of the largest question which took up significant time for of today's session, but it is worth it. So now, like again, one more question which is based on the same question as before. What does the state value function converge to for the policy we started off with? So this is asking us, like we were giving some pi naught in the question itself, right? So what is the value function if we converge to for this policy? So they are basically asking us b pi naught. So this we have already computed in the policy evaluation phase, right? What was this value? Uh, this policy evaluation. So this was for pi naught. It was -10 for laughter and 10 for quiet state. So laughter is -10 and quiet state, and they have used silent. So it doesn't matter. Quiet state, it's 10. So the answer is C. So now I'll move to next question. So, and like apart from the problem which I am giving in this problem solving session, like most of the questions are straightforward and practice assignment and assignment both. You're like, you don't, even if you have just watched the lectures, you just need to pick the option and see. You'll know if you have watched the lectures, like actually seriously. So now the question is, in solving an episodic problem, we observe that all trajectories from the start state to the goal state pass through a particular state exactly twice. So in this such a scenario, is it preferable to use first visit or every visit for evaluating a policy? So this basically means regardless of which trajectory you follow. So all the trajectories from the start state to the goal state. So suppose an MDP is there, there is a start state and goal state, and in between there are many states, right? So regardless of like which trajectory you follow, you go this way or this way or you go this way, you are passing through one state exactly twice. So which assumption is getting violated here? Here this Markov assumption gets violated. So in such a scenario, is it preferable to use first visit or every visit? Like basically like neither kind of, because there the problem itself doesn't follow this Markov assumption. So if the problem itself doesn't follow Markov assumption, then how can we comment on whether like which to follow, whether first visit or every visit? So the correct answer here is neither, because like we don't know, because like, the problem itself is not Markov. So now I'll move to the next one. So in this question, they have asked that which of the following are advantages of Monte Carlo methods over dynamic programming, or MC versus DP. So dynamic programming, we were kind of using transition probabilities, and Monte Carlo, like we weren't using them. So the ability to learn from actual experience, yes, we can do that. If we have a real model, then we can definitely do that. The ability to learn from simulated experience, yes. Like if we don't have access to a real model, then we can use a simulator and learn from the simulated experience. So in lectures also, sir gave an example of games. Like for games, like we have the simulator and we can simulate mind. And the ability to estimate the value of a single state independent of the number of states. So when we are like doing Monte Carlo simulations, like what we are doing, we start from a state and keep on generating trajectories from that state only. Like we don't care about like how many states are there. We simply like keep on generating trajectories and take the average. So the ability, this is also an advantage of Monte Carlo. But in dynamic programming, we have to actually worry about the number of states, because if the number of states are too large, then these dynamic programming methods face what is called curse of dimensionality. So this basically means that as dimension grows, our problems becomes worse and worse. And the ability to show guaranteed convergence to an optimal policy. So in case of Monte Carlo methods, we don't have guaranteed convergence, right? We don't have theoretical guarantees that it will converge to an optimal policy. It's just that it works better in practice. So in practice, it's working better. So we kind of use it. We don't have theoretical guarantees. So the first three are the advantages of Monte Carlo methods over dynamic programming techniques. So if like the reverse question was what the advantage of dynamic programming over Monte Carlo method, would have written that dynamic programming like they have theoretical guarantees, which is kind of an advantage is like it is an advantage theoretically at least. So now the question is for a specific MDP, suppose we have a policy that we want to evaluate through the use of actual experience in the environment alone and using Monte Carlo methods. Okay, so we have an MDP, a specific MDP, and we have a policy that we want to evaluate through actual experience in the environment and using Monte Carlo methods. And we decided to use first variable approach. So first variable approach, what happens is like when we like visit a state first, from then onwards, whatever value we get, we use that value. Even if it gets visited again, we keep on like doing this trajectory. And along with the techniques of always picking the start state at random from the available set of states. Okay, so we are like start state, we are like selecting randomly. Will this approach ensure complete evaluation of the action value function corresponding to the policy? So like we know a like limitation of this method. Like Monte Carlo methods are like kind of like they are biased towards trajectories which are like kind of nearby to the policy, which are kind of generated by the policy. So for the actions and states which are not getting generated in the trajectories which are supplied by the policy, those will be like visited quite less often. So there might be some states which never get visited because like the policy doesn't dictate that. So will it ensure the complete evaluation? No. And this is mainly because of that disproportionate bias of Monte Carlo methods towards policy. So for the actions like which are in policy, like they will be visited many times, but there might be some actions which are not part of policy, which might not even get one chance. So the answer is no. Now the question is, assuming an MDP where the n actions, okay, each of which is applicable in each state. So all the states are applicable, all the actions are applicable in all the states, and pi is an epsilon soft policy for some epsilon greater than zero. So they are asking is, okay, so basically they are asking like, what is the kind of definition of epsilon soft policy? So will it happen that the policy will assign epsilon probability to all the actions if we are starting from some status? Like if we like basically like the sum of the probabilities is phi a s over actions, like for that particular state. This should sum to one, right? Otherwise, like probabilities should sum to one. So in this case, it will go to an epsilon. So now we don't know that epsilon is one by n. So it might be happen that like for some epsilon, it might not be one. So this is definitely not correct one. Now again, like similarly for this one, we have n like epsilon were n for each of them, then it will sum to epsilon. And epsilon, although it's greater than zero, but need not necessarily be one. So this is also we cannot guarantee this. So phi a of s, right, is greater than or equal to epsilon by n. Yeah, like this will make this an epsilon soft policy. And here, like basically we are taking every action with at least epsilon by n probability. So it will be like epsilon. So it like this they have given for any epsilon. So if we take epsilon by n, like I think like there is an overloading of this epsilon. So but if we take epsilon by n as our epsilon, then it will become this soft policy. So this basically kind of ensures that every action at least we take sometimes. So again, like what is this? So this is 1 minus epsilon plus epsilon y. Okay, so this we have seen is, so this is like kind of exploiting a dash might be the optimal action, and pi of a of dash, this is empirically optimal, and pi of a given as is like for all the other actions are with epsilon by n. So this is basically epsilon greedy policy itself. And we know that epsilon greedy policy is also epsilon soft policy. because like either way, like this condition, in C is getting satisfied here also. So for this one, we have epsilon by n plus some positive quantity. So for all the actions and state, like this will. Now this is the next question. So given that L is a contraction in Banach space. So we have been given that L is a contraction in Banach space and asked like which of the following are true. L. L must be a linear transformation. L is what is L? L is the Bellman optimality operator, right? So Bellman optimality operator has what is called as max, and this max introduces non-linearity. So we cannot use linear transformation. It is not a linear transformation, right? L has a unique fixed point. Is this true? Yes, it is true. Because like L actually converges to V star, and this is the fixed point. So the optimal value function is the fixed point, and it is unique also. And we kind of like it for L pi, and in a similar manner, like the proof proceeds for this one L also. So this says that let's see option D first. For every state, L of V of S, so there are some points V and U, and this they are asking for every state. So basically like this they have written component twice, but this we can write simply V as vector, and is lesser than gamma times V minus U. So basically like this is a contraction mapping. This is the definition of a contraction, right? So this happens, and like they have given L is a contraction, so this will definitely move. So if it is happening for all the states, so if something happens for all the states, then this definitely implies that there exists some state. It is either way happening for all the states. So like we can always find some state for which this will happen. So this is also a correct option. So the correct options are B, C, and D. So now I am moving to the last question of this section. So the last question of this section is which of the following is true? So this questions, first option is the Bellman optimality equation defines a contraction in a Banach space. This we have already seen. Yeah, this is true. Bellman optimality equation can be rewritten as a linear transformation, again not. Like, it cannot be because this max where each element like it cannot be done in a linear transformation manner. And the final value estimates obtained at the stopping condition of value iteration will be optimal values. Like, will this happen? Like, will they be optimal? Like, what was the epsilon condition? Maybe I'll go back to the value iteration and go to see here. Like, we had this stopping criteria. Like, was it like if this stopping criteria is followed, will it be converging to optimal one or epsilon optimal? Right? It will be converging to epsilon optimal. So optimal need not necessarily be. This is also wrong. The final policy obtained by greedily selecting actions according to the returned value function at the stopping condition of value equation will be an optimal policy. Again, like same reasoning, it will be epsilon optimal because it is either way getting derived from this one. If this is epsilon optimal, then how can this become optimal policy? This is also false. So I hope like you have understood all these questions. Now like I'll move to demo. For demo, I'll like start sharing another screen. Okay, so this is this one. So I'll first describe the problem. So this is the like same problem as week 4, but like last week we did it for value iteration. Maybe I'll just like this. Yeah. Last week we did for value iteration, and this week I'll show for policy iteration. But the problem which we are considering is the same. So this is like the grade world. There is a grade. This is our start state, which is at the top left. Start state, and this is our like goal state, bottom right. This is our goal. And the main difference from the original grid world problem is that there are some barriers. So it's like some barriers are here, and then we cannot go this way. So these barriers basically mean that we cannot move to that state. So this becomes slightly more complex problem, but this is the setup which we are considering. Now I'll start with the collab notebook. So again, like the goal is to reach the bottom right cell of the grid from the top left cell. And there are some barriers. So like, yeah, one more thing to note is like if the barriers are in such a way that it is not possible to reach the goal state, then obviously we cannot say that it is always possible to reach the goal. There might be situations where barriers are surrounding. Suppose if the very in this grid, the barriers were surrounding the goal state. Here there was a barrier also. Here there was a barrier. There's no way we can reach this goal state, right? So in that case, so reaching the goal state is always not possible. But we will see, like we will use these barriers with a smaller probability so that that situation doesn't occur. Or even if it occurs, it's very rare. And the reward which I have considered here is 10 for reaching the goal and zero other loss. But again, like this kind of reward requires discounting because like this will kind of promote reaching the goal as soon as possible. Because like if this 10 is reached as at a later stage, then this 0.9 like it is getting raised in power, right? 0.9 raised to a square, then cube, then if it is done at a later stage and in the intermediate states it's zero, then this reward will get very diluted. So the total reward will become less. So the agent is kind of incentivized to reach the goal as soon as possible. So you can play around with these reward function. You can also like if you can keep negative rewards also, which kind of ensure that the agent tries to reach the goal state as soon as possible to get like lower to get less negative rewards, right? In that case, you can have discount factor as well. So yeah, agent should try to reach the goal as soon as possible. Otherwise, this overall reward will get diluted due to this discount factor. So we cannot use discount factor one if we are using this reward setup because otherwise, like even if it reaches at the maybe 10th step or millionth step or even the like ninth step or something, the total reward will remain same because there is no discounting happening. So that's why like we need this discount factor. So last week like I showed value iteration. So in value iteration, like suppose like this is the maze like which was generated in last week. So I'll explain this again. Like this was the start state, this was the barrier, right? These two barriers were there. So like basically like in this program, we have to enter the maze size so we can decide the maze size and we have to enter the barrier probability also. So with that's 0.2 probability, like these cells can become a barrier. So in this way, like this value iteration keeps on applying Bellman optimality operator until it reaches the like it kind of converges. So at this point, like it kind of converged. So the path, like once this value function has converged, so we have reached the optimal value function. Now we can deduce the policy from that. And the policy, like there can be many optimal policies, right? Need not be one, but the value function will be unique. So I'll show you how. So this policy gives basically down, down, right, right, down, right. So this is like one path, right? But we could have reached it in a different way also. And in that path also, we would have encountered same value. So here you see 30. So this if we start in this way or we go in this way, then also 30 we are getting. So if we suppose start in this way, 30 and come here 33, then second path like it was getting 33, right? Then if we go down 33 again, then we can either follow its path or we can go separate path. If we follow separate, we go to third state, which is 37. And again, here it's 37 for it, then 41 for it, 5 for it, then 41 for it, 5 for it. Then it goes down, but it could have gone this way also. So it goes down to then 46.67. We also come down 46.67 and then 52. So basically, like there are multiple policies which might map to the same optimal value function. So multiple optimal policies can be there, but value function like optimal is unique. So that we can see in this example also. And also another thing to notice, length of, because like we have designed the reward function and discount factor in such a way that the agent is incentivized to reach the goal state as soon as possible. So if there is a 4 by 4 amazed, then it needs to take 3 steps downwards and 3 steps towards right. So the path will be 6. If it's 5, then it will be 8 because 4 steps downwards and 4 steps sideways towards right. Now I'll explain like how this value equation is working. So I'll just simply show you the main function. So what is happening, like here we have used a different kind of stopping criteria. So this different type of stopping criteria is using theta. Theta means point. Theta is value is zero point 0.3. So basically what we are doing is delta. We are maintaining one delta. Initially it is initialized to 0. So delta basically stores the maximum difference between the, so our value function like at two different iterations will have like different components corresponding to each stage. So what is the maximum difference between those components is delta. So the delta is kind of max norm of the difference between two consecutive value vectors. So this max norm is stored in delta, and if this difference like max norm becomes smaller, so they're like in like slides, like in the algorithm which was discussed in lecture, we were having some sophisticated criteria like in terms of epsilon and gamma. But here we have simply set it to be a constant 0 0.3. If the difference like is max norm difference becomes 0 0.3, then we kind of stop it. So this is our stopping criteria here. So and in the loop like this, we are basically iterating over the states, because like our states has two features now, x coordinate and y coordinate, right? So for I in this range and j in range, we are doing if barrier, then we do nothing, right? We don't want to update the variable, and otherwise like we will simply update the value function. And this we are in this function we are simply using the Bellman optimality operator over the current value function, and it will return the new value function. So now like this is being done state by state manner, right? In like we are iterating over all the states. So I represents x coordinate and j represents y coordinate. So in this was value iteration. So now I'll move to policy iteration. So maybe I'll demonstrate it first. So let's see. So it has asked us to enter the maze size. Maybe we enter 5. Now it asks us to enter the barrier probability. We will give 0 0.1 maybe. Let's see. So in policy iteration, like, there are two steps, policy evaluation and then like policy improvement. So this is our initial maze, right? -1 basically represents the barrier. So we started off with this value function, and we kind of like denote like -1 to denote the barrier. Now what happens is like one by one, it keeps on repeating that loop of policy evaluation, then policy improvement, policy evaluation, policy improvement. And afterwards, it kind of converges. So once it has converged to this one. So it basically says, so there can be, I have told this in case of value iteration also, there can be multiple optimal policies. But value function optimal will be unique, and same thing we will experience here also. So this is just one of the many optimal policies in this case. So this basically says if you are in start state, you move rightways, 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 then downwards, downwards, downwards. So policy basically is right, 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 down, 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 down. So it goes this way. But as we can see, like it could have been, since there is no barrier here, it could have been down, 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 and then right, 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 right. So in this way, like there could be multiple policies. But again, like the same point here, if you go this way, suppose 25.17, 27.97, then 31, then 34. And if you go this way also, we are encountering same values, 25, 27, 31, 34, then 38, 42, 47, 38, 42, 47, and eventually 52. So although like there are multiple optimal policies, but the same value function. Again, like same cost of path is 8 because we are using 5 by 5 matrix. So maybe I'll show you like how this policy iteration works. So policy iteration, like we have this function policy iteration. So I'll demonstrate that only. So we have this policy evaluation function, evaluate policy and improve policy also. So what happens? So basically, like we have set a max iteration criterion also. Like if like we don't want to use too much compute power also. Either way, like we are doing this criterion also. If like the new policy and the previous policy are same, then also we will converge. But this is just to ensure that if it doesn't converge, in 1,000 iteration also, then we will stop. So we are using this max iteration also, and this is the discount factor here. So in policy iteration, like basically what we are doing is like for this max iteration number of time, we are evaluating the policy, then improving the policy, and simultaneously we are checking that if the policy has converged. If it has converged, then we will print the final value function, and we will like kind of break out of this loop. Otherwise, if it doesn't happen, then we are doing some printing, and again like this procedure will repeat. So I hope like you got an idea about policy iteration. Now like I'll share this notebook with you also, so you can try out with different reward function, different this discount factor. Even like you can try to change the stopping criteria and see how it works out. Okay, now like I'll start sharing the slides again. Okay, so demo is done. So what I want to emphasize is that I have shown you value equation, I have shown you policy equation, but this policy equation itself has a lot of variants. Like there are, even sir discussed the generalized policy equation, then we go to some extreme, and there are a lot of variants of policy equation. You can find out them, like one popular one is Harvard policy equation, and there are a lot of convergence results also. So if possible, like in next week's demo, I'll like demonstrate some of these policy iteration. And apart from them, like I even this professor and even me, like we haven't discussed anything about LP, like how to formulate this solving of Bellman optimality equation using LP. And once we have like formulated it using LP, so basically like we'll have an objective function and some constraints. So basically, like this is not really a reinforcement learning kind of problem. It's just that we have a problem in MDP planning. We are like using this technique. This is a technique from optimization, right? You might have studied a course on optimization in which linear programming is there, or in which constraints are linear and all those conditions are there with respect to linearity. So this like solving of Bellman optimality equation is converted in an intelligent way to an LP, and the solution of this LP kind of corresponds to our optimal behavior. And this can be done in two manner, as is the case with any LP problem. You can either formulate primal or dual. So all those equations are there. Maybe if you want to have a look, you can look at this LP formulation also. So these are the three ways in which planning is done. Remember in planning, like we have access to this transition probabilities. So it is kind of computation problem only. Now I'll move to the last segment of today, which is the assignment. So for assignment, again, I have mentioned this before also, but like the questions in both the programming assignment and even the assignment, both of them are like quite straightforward. Like not much calculation is happening because like the content which are you are getting taught nowadays, like in current lectures, like is more towards theory. So like the questions will be factual based, not many numericals kind of question as we were used to in bandits and all. So this question says in policy iteration, which of the following is true about policy evaluation and policy improvement steps? Again, like this is square. Circle means option, right? Remember this, like sometimes many students make a mistake. And this means multiple option, correct. Okay, so this basically says that uh, there could be more options, correct? Could be one also, but at least one. So the value of the states that are returned by policy evaluation may fluctuate between high and low values at the algorithm runs. So no, like this doesn't happen, right? Because eventually, like we are moving to pi to some pi n to some pi n plus one. And this pi n plus 1 is chosen in a greedy manner. So we are like kind of moving to a better policy in each step, or at least equal, not if not better. But this would not fluctuate. It won't go low, right? We are moving towards optimality, so it won't fluctuate. So this is definitely wrong. Now, PE returns the fixed point of L pi of n. Is this true? Like policy evaluation, what does it use? It uses Green's equation, right? And it kind of returns the fixed point of this L pi. So this is true. Now, PI can policy improvement can randomly select any greedy policy for a given. So does this like happen any greedy policy? No, it doesn't select any greedy policy. It has to be greedy with respect to all the components, right? So this any is the issue here. So what happens is if you select like basically like I'll show you like how this option is relevant. See, while we were doing this policy improvement here, I went with this action, right? If in the next section, this is also a greedy policy, right? If I took this action and this action for quiet state, this is also a like a greedy policy with respect to, but I have some tiebreaker criteria, so I cannot go with any greedy policy. If I fix some tiebreaker criteria, I need to stick with it. So this is what like removes like that any. So we cannot go with any. We have to like have some consistent tiebreaker criteria and then stick to it. Otherwise, like there will be oscillation. So any PI can randomly select any greedy policy for a given value function. Not any. Policy iteration always converges for a finite MDP. So since this is assignment and you guys still have deadline till I think 28. Yeah, 28. So I won't be giving you answers, but you know the answer. Like this has been discussed in class also. Will it always converge for a finite MDP? Although like there was a not a rigorous proof, wasn't covered for this policy iteration, but there was an intuitive proof, right? Which said in terms of finite number of policies when we are improving, then eventually we should converge. Mm, Now I'll move to the next question, which says, now this is corresponding to Monte Carlo approach for policy evaluation. Okay, in a way. So suppose the states are S1, S2, S3, S4, S5, and S6. So these are the six states, and terminal state is also there. So they are denoting it by terminal underscore state, and you sample one trajectory as follows. So this is our trajectory. We are moving from 1 to 5 to 4 to 6 to some terminal state. So, you know, like what is the special thing about this terminal state? So terminal state can only have incoming transitions. It doesn't have any outgoing transition. This is not allowed in terminal state. So terminal state is kind of like a sink. Like you might have studied in thermodynamics, like in sink, like we can put up, like you can think like black hole or something. Like you just keep on going there, but never come out of it. So this is a terminal state. Like if we reach some terminal states, then we kind of end the episode. So that is the intuition behind this terminal states. Suppose in the game of chess. So if we are like playing multiple games, like win could be one terminal state, lose could be one terminal state, or eventually like if timer runs out or like the both the players agree on a draw, then draw could also be a terminal state. When one of these three happen, we will kind of end the episode and we can play again. So these are the terminal states. So which of the following states can be updated from this sample? So again, this is a multiple option correct. So like this is asking which can be updated, not which should be updated. Like we have seen like problems which can arise if we like do this kind of update. Like there could be an in a bias can get introduced. You remember this example in which like one trajectory is getting generated and there is some rare event which happens here. But if we like use the same for two times, Right, then this, suppose this where event was 1 in a million, but now it's getting counted twice, or if we are doing many times, then it is getting counted multiple times. So this thing changes here. So rare events might act as if they are not that rare. They can happen frequently. So in this way, like this distribution can change. So like we usually don't want to do this kind of thing because like bias gets introduced. But the question is asking not like whether we should do or we should not do. The question is asking which can be updated, like not the consequence of that update, but which way can be updated. So any state like which is appearing on this trajectory can be updated, right? So what are the states? So you can derive that easily. Uh, S2 is not there. Apart from S2, all of that we can update. So now I move to the next question. So this next question says, again, with respect to Monte Carlo, so which of the following statements are true with regards to Monte Carlo value approximation method? Again, multiple option correct. So to evaluate a policy using these methods, a subset of trajectories in which all states are encountered at least once. So yeah, if we are able to get a subset of trajectories, such that like we visit every state at least once, that is enough to update all the state values. Right, in Monte Carlo, like there was a question before that if we are in some state, we don't need to worry about the number of states, right? We can independently do for this system. But what was the issue with this one? That like there might be states which we never visit. But here, like they have given us a subset of trajectories which kind of ensure that every state is visited at least once. Some might be visited just once, but that is enough to update all the state values. So yeah, this is correct. So Monte Carlo function approximation methods need full knowledge of the model. So this, like, I think if you have watched the lecture, you can easily spot this. Do they need full knowledge of the model? Full knowledge of the model means do they need access to transition probability? So in like this planning, our model is basically an MVP. This is like in RL itself, our environment. So in RL, we have this agent, which is like agent can be anything like a robot or a human or even an algorithm. And we have an environment. And this agent interacts with this environment. It takes action on this environment, and the environment comes up with next state and the reward. So this environment itself is modeled using an MDP. So what this full model means, like we have access to all the 5 components of an MDP, which are set of actions, set of states, and transition probabilities, reward function, and gamma. Do we really need like complete knowledge? We can do without this transition, right? We don't need this. And also like we don't need the knowledge of the full model. We can use a simulation of the model also. Just we need some simulations. So there is also like need, do they need? Not necessarily. If it's available, then well and good, but they don't need it. So Monte Carlo methods update state value estimates only at the end of an episode. Obviously, like this has, so end of episode is associated with like when we are like we have reached a terminal state or something. So or like there could be some criteria in which like we ensure that the maximum length of a trajectory could be 1,000 steps. So there are different type of stopping criterias, but like yeah, we don't update in between, right? We like first generate the trajectory till the end, then like keep on summing over this trajectory, and then at the end we will update the value. So this is happens, but then there was a method which was discussed well before also, and it is like coming in week 6 also, which was temporal difference, in which like we were not just at the end of the episode, even within the episode at step. Suppose we are moving from one state to next state as this. Even this transition, we can make an update. So this is called temporal difference learning, PD update. So this has been discussed before also, but again, like it will be revisited in week 6. So in that, like we can like do updates at step level also. but Monte Carlo methods update state value estimates only at the end of an episode. Yeah, this is also true. So again, like using this, you can get to the answer for this question also. So now I will move to fourth question. So the again, for like there are a lot of Monte Carlo questions. So in every visit, so this is pertaining to every visit Monte Carlo. Multiple samples from for one state are obtained from a single trajectory. Okay. So yeah, like this is the definition of every visit. Like in first visit, like we are simply like, once we first visit some status, then we start like using whatever we calculate from that state and sum it up, and it can be discounted also. That is not an issue, but we keep on summing. You remember this expectation was there, so we keep on until the terminal state is reached. But in every visit, what happens? Suppose if we are in some state, and again if we see this state again, and if we see this state again, so first estimate will be the entire one, second estimate will be from this point, and third estimate will be from this point, and then we kind of average these three estimates. So in limit, like if limit and like if we are doing till infinity, like infinite number of samplings and all, like both will converge to the same thing. But in practice, like there are some differences because obviously we don't do till infinity. So you can see visually also like this sum, if like is just one, so it will be suppose if it's 10, and maybe it's 10 for this one, and 6 for this one, and 4 for this one, then for every visit it will be 20 divided by 3, and it will be 10 for this one. But if we do multiple times, then like this limit kind of converges, so both will converge to the same value. But yeah, like if we don't do infinitely enough, then there is a difference we can see here. So what does this ask? Which of the following is true? This is regarding every visit. So in every visit, Monte Carlo methods. Okay, so this I have already discussed before, like terminal state, right? So some bias was getting introduced, right? Some rare event is there, and it gets counted twice. So the main point here is the bias is there, which wasn't there in DP. Right? In DP, it wasn't there, but as soon as not just in DP, even in like first visit, if we were using first visit, then if some event is rare and we are not counting it multiple times, we will count it only once, right? So in that way, like this bias was getting introduced, like if suppose this some rare event is here, then it was getting counted 3 times in this case. So in that way, bias is getting introduced. So the options are like this is a single option, correct? So there is increase in bias of the estimates, and the seems to there is increase in variance. Okay, so bias variance, you might know about this one. Bias variance trade-off. Like this is a concept from classical machine learning, but this is applicable in so ML is like kind of divided into supervised learning, unsupervised learning, and reinforcement learning. So this kind of these the concepts of ML like bias variance trade-off like apply to all of them. So basically the concept is if bias increases, then variance decreases. And if bias decreases, then variance increases. That's why we need some kind of sweet spot. So basically like it goes like one decreases, other increases. So this is the sweet spot which we want. And like there are like these are like x-axis basically represents complexity of model. So if we move towards complex and complex model, then like the variance kind of increases. And if we are simple having simple enough models, then the bias is more, but like we generalize better as we move towards complex model. But if we are too complex, then this variance will also increase. So this bias and variance have a kind of inverse relation. So there is an increase in variance. So increase in variance kind of implies decrease in bias. No, this doesn't. It does not affect the bias or variance of the estimates. I mean, this is also false. Both bias and variance of the estimates increase, like they are in kind of inversely related. So both, simultaneously increase, right? So now I'll move to fifth question. So after many questions on Monte Carlo, now this question is about dynamic programming. So what it is asking is false. This thing to note is false. It is asking about false statements. So about solving MDPs using dynamic programming. So if the state space is large or computation power is limited, it is preferred to update only some states through random sampling or selecting states seen in trajectories, right? So this actually is true, right? If we have very large state spaces and our computation power is also limited, we kind of sample some states and update those states only. And like, what was this called? RTDP, right? Real time dynamic programming. So some states we were getting and we were selecting those states which are seen in trajectories. So this kind of ensures that the states we are seeing in trajectories are the states which will occur more and more. So we kind of prefer to update only those states. And there might be some states which rarely get visited. So if some states are really getting visited, then like we don't worry much about them. So this is true. So the question is to asking about false statements. So this is not it. Knowledge of transition probabilities is not necessarily for solving MDPs using dynamic programming. So dynamic programming, like both policy iteration, value iteration, although LP is not covered in the lectures, but like both of them require these transition probabilities, right? So like this is false. In fact, MC methods, they don't require transition probabilities. Also not just Monte Carlo methods, but when we move to full RL, like which is control setting. In control setting, we don't have access to this transition function. So there are ways of like doing it. Either we do it in a model free manner or model based manner. So in model based, we kind of estimate this transition function. So there are algorithms in which we will first like sample enough times and we kind of approximate this transition function. And once we have approximated it well enough, then we will kind of run our planning algorithms on this. And then there are model free approaches in which like we work like in an online fashion and we don't need to approximate this transition function. We work like TD updates. So TD updates is again model free algorithm and which works in an online fashion. And we will like soon study learning SASA. SASA is basically state, action, reward, state. Like this is next state and next action. And so this is the like short form of SASA. And there is one more called expected SASA. Also, like these are like value function based methods. So there is one more class of methods which are policy based, which work in the policy space. Policy function, policy not function based methods. So you might have, we have already studied this reinforce, right? Reinforce like it was working in the state of like in the space of policy. Then there are other methods like policy gradient and many other variants. So those work directly in the space of policies. And then like there is one more class which kind of combines these two value-based methods and policy-based methods. And that is called actor critic. So what happens in actor critic? So there is a module actor, which is kind of policy-based, and there is a critic module which supplies criticism in terms of value functions. So like this is the like basic overview of what is coming up next in the course. So the knowledge of transition probabilities is not necessary. So it is like false statement. In like classical DP, we need it. Transition probabilities is needed. So now the next question is methods that update only a subset of states at a time guarantee performance. So this is like mainly like if you consider generalized policy equation. So methods which update only a subset of states at a time guarantee performance equal to or better Like there is no guarantee, right? Because we are updating only a subset of states. And it is saying that we are guaranteed performance equal, not just equal, but better performance than classic DP. This is also false, right? So again, like you can deduce like which of these are false. So multiple option correct. You have to take the only false statements. Again, like none of the above can become false, but you can take it. So now, as I already mentioned GPI, next question is on GPI. And here we have to point out correct statements about the GPI. And again, like multiple option correct. So what is happening in this? GPI lets policy evaluation and policy improvement interact with each other regardless of the details of the two policies. Yeah, like so basically like this loop, we are kind of looping some stopping criteria you can start. And what we are doing is policy evaluation and policy iteration. We don't care about like it can update all or it can update partially like some subset, right? We don't care much. It again improvement also it can update some of the states of the policy and maybe partially just a subset. So like how they are working, we do not care much regardless of the details of the two processes, but it kind of lets to them to interact with each other. Even like the subset which each both of them are selecting, they need not be same. It can select some subset which is kind of disjoint. Like both of them can select separate disjoint. Like there is no common states between them. So yeah, this is true. GPI lets policy evaluation interact with each other regardless of the details of the two processes. Now, second question is before convergence. So this is before convergence. And we haven't converged yet. The policy evaluation step will usually cause the policy to no longer be greedy with respect to the updated value function. Yeah, like, see, the one thing to note is this is not asking about not value, like general policy iteration. Like we saw, like general, I mean, common policy iteration, like the algorithm which I showed on this slide. So maybe we can call it default policy iteration. So if this is the default policy equation, it is not talking about this algorithm. So this algorithm has some guarantees, right? It is talking about generalized policy equation in which like we can use some subset. So this thing is important to keep in mind. So this statement would have been true if so basically what is saying before convergence will usually cause the policy to no longer be greedy with respect to the update. So but in case of default policy iteration, it will be greedy. But yeah, here it might happen that it will no longer be greedy. And why this will happen? Suppose if like it selects some, like both of these select some subset S1, S2, and both of them are disjoint. There is no connection with them. And it might happen that it is no longer greedy with respect to the updated value function because the value function got updated on a different set of states. And suppose in policy improvement, we improved on some other stage. So it is no longer greedy with the value function which is updated on these states. So it might happen. So this is also true. So GPI converges only when a policy has been found which is greedy with respect to its own value function. Yeah, like this holds for all the policy iteration, whether it's GPI, well, it will converge only when like we will find a policy which is greedy with respect to its own value function. If it's greedy with respect to its own value function, definitely that has to be optimal policy, so it converges. So I mean, like all the three options are correct till now. Last one, maybe you can decide. Otherwise, I'll give out the answer. So the policy and value function found by GPI at convergence must be optimal. Will it be like if for default policy iteration it happens, right? Because like even though like there could be multiple optimal policies, but all will map with the same value function, optimal value function. So will this happen for GPI also? That you need to think, and simultaneously you can deduce the final answer. So okay, so now we are back to Monte Carlo. So what is meant by off policy Monte Carlo value function evaluation? So like generally like till now we didn't encounter this off policy. We were working on policy. So what on policy means is, like, suppose if there are two policies, pi 1 and pi 2. One is used for generating trajectories, or you can say samples, and another is like which we want to evaluate to be evaluated. These are policy. So in on policy, this pi 1 and pi 2 are same. So we are using the same policy which we want to evaluate to actually generate the trajectories. But in off policy, like you might have watched the section of off policy, there was a video in which like we use the concepts of importance sampling and all. So what was the difference in off policy? So this is a single option correct. So again, like one thing to note is like in Monte Carlo value function evaluation, this is considering evaluation. So learning options definitely are not there. Policy being learned. We are not interested in learning as of now, currently. Currently, we are only interested in evaluating the policy using Monte Carlo like simulations. So kind of averaging over 20 So in on policy, those are same, but in what happens in off policy? So this corresponds to on policy, right? So again, like you can see what is the answer. So in off policy, they are different. So this is done using importance sampling, in which like we want to take the expectation with respect to distribution P, but we know it's easier to sample from some distribution Q because of CDF. Like if CDF of this P is hard to calculate, then we can sample from Q, and then like we have that importance factor, right? P upon Q. So like using that importance factor, we can kind of approximate the expectation with respect to P using this Q. So this is the concept of off policy. Although like there's a one more lecture on this in next week. So now the last question is, for both the value and policy iteration algorithms, we will get a sequence of vectors after some iterations. So say V1, so this is the sequence of vectors for value iteration. Okay, and dash one is the sequence of vectors for policy iteration. So which of the following are true? Hmm. For all Vi belong to Vi V2, there exists a policy for which Vi, like, I think this is an incomplete question. It's a fixed point. So this is a complete statement. So will it happen for all Vi? There exists a policy. So this is corresponding to values functions. So you remember, like I mentioned it in one of the previous question also, this value function, like space of these value function, it contains all value function, right? But apart from these value function, there might be some extra functions for which like those points don't not are like the value function. There might be all value function will definitely be in this V space, but there might be some extra functions which are do not correspond to a value function. Extra functions which might not be value function. So will there always exist a policy for which some point Vi is a fixed point? So like there may not exist, right? So this seems correct. So this is like first and third option are corresponding to value iteration one. So there may not exist a policy for which Vi is a fixed point, right? Or suppose if this maybe I'll take some VF kind of point. So this point is F. So F stands for like some function, which is not a value function. So this point is residing in this space, but this is not a value function. So it won't corresponding to some policy part. So there might be possible that there may not exist a policy corresponding to this point. So although it might be a fixed point. And now for policy iteration. So for policy iteration, the options are these two. So automatically, if this is true, then this is false. Now what happens? for policy iteration, will it happen that there exists a policy for which VI dash for all? And so in policy space, we are working in space of policy. So suppose this capital pi denotes and small pi is belonging to this policy space. There will always exist a policy for which like VI dash is a fixed one. So we are working in a different space. So again, like this will be correct and this will simultaneously make the other option incorrect. In this way, you can get the answer. So this is the like kind of subtle difference between these two, the spaces they operate on. We like value iteration is operating in this space where some extra points might be there, which might not correspond to value function. But by like this policy iteration is operating in the space of policies. So in that case, like there are no extra, like this basically contains policies only. There are not points which do not correspond to a policy. So in this way, you can get the answer for this one. So now again, like the reading material. So for reading material, like chapter 4 is dynamic programming, and this chapter 5 is Monte Carlo. So basically, I'll show you the book first. Real. I'll share um, Mozilla just a minute. So I'll go to the index. See, bandits and all we are done. Finite MDP like this is also done dynamic programming. So for dynamic programming like this policy evaluation, just a minute, I'll use this line. So for policy evaluation, it's done. Policy improvement, policy iteration, value iteration is done. Asynchronous DP is also done. Generalized policy iteration is also done. Then efficiency of dynamic programming. So basically, like this entire chapter is completely, as I mentioned before, also like from chapter 3, you can read all of the sections. There is no reason to wait. Like you can do even some advanced reading. And for with respect to chapter 5, although like we have covered till Monte Carlo prediction is done, Monte Carlo estimation of action values. So this you can read. Control, we have started with exploring starts. So this off policy and all, like why, although like important sampling has been covered. So this will start in week 6, but you can maybe read up these sections also. And afterwards, like in next week, like there will be a movement to TD methods. This you can, all this you can read. So okay, then like I'll be sharing these note this notebook to you, like which contains code of value iteration and policy iteration. And this notebook you can try out with different reward function also, and also some different discount factor and some different stopping criteria. Also, like you can play around with size of maze and also the barrier probability. So this is just for your learning. You can do that. And I think, yeah, that's it from my side for this week. And if you have, although like this is a kind of recorded session, so you didn't get the chance to interact with me, but if you have any queries, maybe you can ask me in the next session, which is scheduled on uh, next Tuesday, not this Tuesday. So basically the session on 27th, like this moved to 23rd, right? And the next session was actually on, next session is on 5th. So now on 5th, we will meet 5th or 4th. Let me see. Yeah, it's 5th. So 5th March, which will be a Tuesday. From now on, like all our sessions will be on Tuesdays. So you can join then, and this will be corresponding to week 6. So it's essentially like almost 10-12 days from now. Okay, then. So I think that's it from my side. I'll close this session. Thank you, everyone. Now I'll stop sharing my screen. Stop the recording.